Welcome viewers, this is Mr. Odingo. I want us to move on to the next part of our lesson, that is strength of ionic bonds. In our previous class, we were able to look at the introduction to ionic bonding. We were able to look at how to be able to draw the ionic bond of different compounds, and we also move forward to look at what we call the giant ionic structure. Today we want to look at the strength of ionic bonds. Now, strength of something, when something is stronger, you will need more energy to break it, and that is why when we are looking at the strength of ionic bonds, mainly we will be talking about melting points. The compounds, the ionic bonds or ionic compounds whose melting points are very high, means that the strength or the electrostatic force of attraction between those two ions are very strong. But today we want to look at how do we explain that. In this case, melting point will just be able to, it's just a manifestation of the bonds, of the strength of the bonds. But we want to know what explains, how do we explain those particular melting points. On the table I've drawn here, I want us to be able to see this other side. I've indicated things we call the lattice energy. The lattice energy is the force of attraction that is holding the ions together in ionic bonding. We know that we have other things like bond energies, which we talk about in covalent bonds, but in this case we have what we call lattice energy. So from here we can see that as we come down in this category, we have lithium fluoride, we have magnesium fluoride, we have magnesium oxide. We can see the lattice energies increases as we come down here. So lithium fluoride has the lowest lattice energy, that is 1031 kilojoules per mole. We have 2957 kilojoules per mole for magnesium fluoride, and then we have 3791 kilojoules per mole for magnesium oxide. Now we want to understand why this is happening this way. It means that if you are able to melt these compounds down, we'll spend more energy melting or breaking down magnesium oxide, and that energy will be 3791 kilojoules per mole of magnesium oxide. Now, the explanation as to why magnesium oxide is having the highest lattice energy or melting point for this matter will be able to be explained with, we have to use two factors here. There are two factors that we'll consider when determining why magnesium oxide has the highest melting point or has the highest lattice energy. So one of the factors is, number one is the size of the charge. The size of the charge, the size of charge on an ion. The size of the charge of an ion. Now when a charge is bigger, for example, we know that lithium has a charge of +1, magnesium has a charge of +2, aluminium has a charge of 3+. We can say that in this particular case, the charge of fluorine here, or lithium, sorry, is the lowest, and then aluminium has the highest charge. So when we look at them just the way they are, we expect that aluminium here will be able to project a much more stronger force of attraction than lithium. I'm talking about that if we put the other factor constant, assuming we are just looking at their charges. So we are going to look at the charge, this is the slowest, and this is the highest, so aluminum will be able to actually have a stronger force of attraction. Now, the second factor that we look at here is what we call the size of the ion. The size of the ion. The size of the ion, we know size of the ion, the variable here that gives us the size of the ion will always be the ionic radius. The ionic radius. Now, when an atom is bigger, it means that the force of attraction, the nuclear force of attraction, is much more lower. The force of attraction pulling the outermost energy, electrons in the outermost energy shell, will be much more slower compared to an ion with a small atomic radius. So And we know that when we talk about the outer energy shell, we are talking about something of a sphere, in something of a sphere. And we know that a sphere is, the surface area of a sphere is 4 pi r squared. So we can actually say that the smaller the surface area, the bigger the charge. It means that the charge, the strength, the force of attraction here is inversely proportional to the surface area. So if I have here force of attraction, let me say F, will be inversely proportional to the surface area of the ion. And when I'm saying in this case, we are assuming that ions are spherical in shape. What about the first factor that we talked about, the size of the ion, the size of the charge on the ion? The size of the charge on the ion, I said, the bigger the charge, the stronger the force of attraction, and that is very true. So here F also will be directly proportional to the charge. Let me say the charge is Q. So if we bring these two factors together, because these factors will have to work or interact with each other together for an ion. An ion is spherical and also it has a charge. So those two, we cannot talk about the charge in exclusion. We have to talk about both the size of the charge on the ion and the size of the ion, that is the radius of the ion, together, both of them. When you bring both of those factors together, then we are talking about a concept called the charge density. Charge density. Charge density, therefore, describes the force of attraction that an ion will actually project when it's pulling an ion or a cation to itself. So in this particular case, I've talked about factors that affect the force of attraction that an ion can really project or manifest. And we have talked about those two factors are the size of the charge on the ion and the size of the ion itself. And I've said that an ion may be spherical in nature, so we talk about the size in terms of surface area. But again, if we look at these two factors, now that this is force of attraction directly proportional to the charge on the ion, and the force of attraction also is inversely proportional to the surface area of the charge, so we can actually bring in the concept of charge density. And therefore in charge density here, we can estimate the charge density by saying charge density equals to charge density of an ion equals to, that is going to be charge. If you look, we can see that the charge here, or a force, charge density in this case, I want you to imagine it in terms of force of attraction. The electrostatic force of attraction here is what I'm referring to as charge density. So this charge density, or the force of attraction here, it was directly proportional to charge, and you can see that, and also inversely proportional to the surface area, of that ion. So we are going to have something of this particular nature here. Now, we usually just estimate. This formula will just be able to help us to be able to group or to arrange ions in terms of their strength, the strength that they project. We can calculate this to tell us whether lithium has a bigger charge density than magnesium and so on. So in this particular case, we know that 4 pi here is a constant usually. It is going to be the same whatever the radius. So we can simply assume this one, because when you are calculating this factor, it always affect every other charge. If you divide a charge by 4 pi r, in other words, we are just talking about the variable here that is going to change from time to time is radius squared. So we can talk about charge density, therefore, is an approximation of the charge itself, charge on the ion, divided by radius squared. So we can say that the charge density of any ion, is directly proportional to the charge, but inversely proportional to the square of its radius. So this is charge density that we have there. So if someone talks about us calculating the charge density of fluoride ion, lithium ion, sorry, we are going to say the charge density of lithium ion in this particular case, charge density of lithium ion, can be approximated to be, the charge on lithium is 1 over Radius of lithium is 0.076, so 0.076 squared. If you calculate this one, you will be able to get what we are referring to as the charge density. And we can be able to calculate the one for magnesium so that we can compare between lithium and magnesium, which one is going to give us a bigger charge density. Let's try to see one for magnesium. The charge of magnesium is 2, positive 2, over its radius is 0.072 squared. We can see that the value for magnesium here is 2. And the radius here is even much smaller than the radius of lithium. So what we are going to see here is the value we are going to get for magnesium will be much bigger than the value we are going to get for lithium. And therefore we can say that the force of attraction that magnesium will be able to project against the anion that it has, maybe we are using fluoride, lithium fluoride and magnesium fluoride, we expect that the charge, the density of this one will be higher than the density of this. And if the density of magnesium is much higher, in this case fluorine, fluoride ion and fluorine is a constant factor here. The only difference is lithium and here is magnesium. There are two things that are acting in play here. One, the radius of magnesium is smaller, and we said that the smaller the radius, the bigger the charge density. So this radius is smaller for magnesium. That's advantageous. It means that already we are going to have a bigger charge density for magnesium. And again, you can see the charge here. The charge on the ion of magnesium is positive 2. That is also going to be able to almost multiply. And that's why you can see that due to the charge densities, magnesium fluoride has a lattice energy of 2957 kilojoules per mole, and this one is 1031. You can see that actually the interplay between the charge here and the radius here is producing for us a lattice energy of almost more than 2 times that one of lithium fluoride. So that's what we are going to look at when we are looking at this the force of attraction or the strength of bonds. I've said they are an interplay of 2 factors, the radius of the ion and also the charge on the ion. Now let's look at what is happening here. We have been able to explain actually what is going to happen between these two, and due to the calculations we have had from this to this, we are able to see, and also the charge. We know that in this ion here, this is plus 1, this is minus 1, this is plus 2, this is minus 1. So we can see that this one is much bigger than this, and we said that the conclusions we made earlier, the 2 factors that affect the charge density here are the size. The smaller the size, the bigger the charge density. The bigger the charge, the bigger the charge density. So the bigger the charge here, the density will be bigger. And also the smaller the size. You can see the sizes here. This one is much smaller than this one. Again, here we are going to have the size here producing for us a bigger charge. And that big charge density is also resulting into this particular difference that we are seeing here, that this one will require a small amount of energy to break because of a smaller charge density of lithium, and this one here will require a much bigger energy to break because of the bigger charge density we have calculated here. Now let's move to magnesium oxide. In magnesium oxide is an interesting case because we are now seeing, in this case here, the charge of lithium was doubling from positive 1 to positive 2. But fluoride ion was maintained here. In this case, we have doubled both of them. We have doubled the charge of magnesium here. We have doubled the charge of oxygen. And we can see again what is happening. It's now much more bigger than this. Now the difference we can see here is not due to the magnesium ion, because that's a constant factor now, but it's due to the change in the fluoride ion to oxide ion. In this case here, magnesium ion is positive 2 and oxide ion is negative 2. So we can see here the doubling of these charges cause some changes or some increase in the lattice energy. We can be able to calculate, if you want to go to calculate charge densities here, we can calculate the charge density of this, the sum for this and this we add. We come here, we add. Then we come here, also we add. We are going to see that finally the bigger charge density is going to be with magnesium oxide, followed by this, then followed by this. You can try that at home. You can try to calculate that so that you can tell which one is bigger. Now, moving forward, I want to continue to what I call polarization effect. Polarization effect is what I want to bring in here before we continue. But before I go to that polarization effect, I want to talk about something briefly called isoelectronic ions. Isoelectronic ions, I want to see how do we deal with isoelectronic ions, or what are actually isoelectronic ions. What are isoelectronic ions? The word iso means the same, isotonic. The word iso always means the same in science. So when I say isoelectronic, electron, so meaning I'm talking about something iso, same electrons. So we are talking about atoms or ions with the same number of electrons. In this case, let me talk about magnesium ion. Let me talk about sodium ion. Let me start with sodium ion, then magnesium ion, then aluminium ion. Sodium atom has 11 electrons. Once it loses one electron, then sodium ion becomes has 8, meaning 10 electrons. That's electronic configuration. This is electronic configuration. This is, let me say, number of protons. Let me just use the word P, the letter P. So number of protons here remains 11. But when you go to magnesium here, the electronic configuration will still be 8 because magnesium is number 12. It will lose 2 electrons to be stable. Losing 2 electrons meaning it will be having 10 electrons remaining. The number of protons still remain 12. Aluminium is 8 still because it will lose 3 electrons, but the number of protons remain 13. You see here we can talk about sodium ion, magnesium ion, and aluminium ion being isoelectronic ions. Why? They have the same number of electrons. That is 10, 10, 10. And because they have the same number of electrons, they also have the same electronic configuration. And you can see 2, 8, 2, 8, 2, 8. Let me move forward to elements like nitrogen. We know nitrogen is number 7 in the periodic table. Now nitride ion will be having ion of 3 minus. And we know that nitride ion, the electronic configuration will be 2, 8 because it is number 7, 2, 2, 5. For it to be stable, it needs to gain 3. So that will be 10 electrons. But the number of protons will be 7. When we come to oxide ion, oxygen is number 6 in the periodic table. That is number 8 in the periodic table, sorry. That is 2, 6. So 2, 6, it will gain 2 electrons. That will be 10 electrons. That is 2, 8. The number of protons are 8. Then we have fluoride ion. Fluorine is number 9. So fluoride ion will be formed by gaining 1 electron. That is having electron arrangement of 2, 8 still. That is 9. So that is what we have. So we can talk about all these six ions are isoelectronic ions because they have the same number of electrons, 10, 10, 10, 10, and 10. And also they have the same electronic configuration. If they have the number of electrons, they must have the same electronic configuration as well. We are going to see that the atomic radii or the atomic radius of these elements, let me just indicate them down here so that we can see. These are the atomic radii of these ions that we have here. We can see that the metal ones are much smaller than the non-metal ones. The reason is we know that when these things loses electrons, there is no problem of repulsion, electron to electron repulsion case, and therefore there is no bulging out of of energy shells. That's what is happening here. That's why the atomic radius appears to be much smaller, although all of them have the same number of energy shells. When you come this case here, nitride ion here or nitrogen here had to gain the largest number of electrons. Once you gain the largest number of electrons against 7 protons, there's going to be the electron to electron repulsion will be much more greater, which will again weaken the nuclear force of attraction, forcing the nitride, the size of nitride ion to bulge outwards, making it much bigger than the counterparts in the metal ions. The same happens to this one. This one gains the 2 electrons, so there's some repulsion, again bulges, and then fluoride gains only 1, and that's why you see that the size of fluoride ion is much smaller than this one and this one. The sizes are much bigger than this one, as I've said, due to electron to electron repulsion forces. Viewers, that is all I can say. We can be able to compare these things. When you are told to explain what isoelectronic ions are, just be able to write the electronic configuration or find the number of electrons that they have, then you will be able to determine which pair of ions are isoelectronic. Thank you very much. Next, we are going to look at how to explain what we call polarization and electron densities.